Hello and welcome. I'm not just from the Norwegian University of Science, but also Technology, also known as NTNU in Trondheim. My name is Stein. I'm a master student with the Physics department, and I'm going to talk today about the aspects of implementing CubeSat-ready electronics for a radiation monitoring device. Alright, first the outline. There's not much time, so I have to chase you a few things, and we can take very detailed questions for the coffee break, for example. We're going to first talk about the science background. Why do we need radiation monitors? Then I give you a brief introduction into the electronics. Then you're being told the challenges we have to meet, the opportunity given, and my project and the conclusions from it. First, the science. One application for radiation monitoring is to study space weather. This is the environment in which we have our satellites and astronauts, so this is something important to know. And from a scientific point of view, it is the study of high energetic particles from solar storms, namely protons and electrons, and a few other heavy ions. We can investigate the interaction with the Earth's magnetic field, and we can use it as a measure to protect satellites and astronauts in space. On the right you see a depiction of the Earth's magnetic field interacting with a CME from the Sun. Another scientific aim you can investigate with a radiation monitor are cosmic rays. These are extremely energetic particles, usually from outer space, so from galactic or extragalactic origin. Mainly protons and other heavy nuclei. The origin not being really yet has to be found. Why do we want to study cosmic rays in space? This can be done on the ground, but there we only see secondary particles due to interactions in the atmosphere. So by looking at cosmic rays in space, we can actually study the primary particles. So this is a nice complementary technique to already existing ground-based observatories. And this enables us to connect our satellite research with high-energy particle physics as being done not so far from here in Geneva at CERN. Alright, and there are lots of interesting subjects to be studied in this realm. Now a brief introduction as to how we can actually detect high-energetic particles. There are many techniques, however I will focus today on semiconductor sensors. In this case I will show to you an example of a silicon diode. You see on the top the graphic. So you apply an electric field to an intrinsic semiconducting material, and then you've got this high energetic particle entering this material and creating, if it has sufficient energy, electron-hole pairs, which in turn create a current pulse, which can then be detected by electronics and analyzed. And the total charge, so the total number of knockout pairs, will tell you about the particle energy, which is important, to not just study something has been hit, similar to as you have measurements in the Geiger counter, but you can also analyze the energy of these particles. Alright, and the purpose of the electronics is to take this physical input signal and convert it into a digital signal for further processing. The front-end electronics processing steps are as follows. So you have what you have seen in the previous slide in the figure is the sensor and the radiation creating this very short time, so we're talking nanoseconds, pulses. These are then being fed into a low noise integrating preamplifier to increase the signal, because we have just several thousands of tens of thousands of electrons, which is not much in charge, and this needs to be amplified. And that signal is then furtherly shaped in a pulse shaper in order to increase signal to noise ratio, so it's a noise improvement as such. And then afterwards we carry out analog to digital conversion in order to be able to deal with it using digital electronics and compress the data. And this is being handled by a digital bus system, which then interlinks to the onboard computer system. All right, the challenge. We're here on a CubeSat Symposium, so we have a small satellite, low mass and low power. However, these sort of instruments usually require a lot of power, so we have to counteract on this. And yeah, let me go through this. Yes, so here you have an example of actually one double CubeSat from our university called NUTS. It does not have a radiation monitor as an imaging device on it. And yeah, it just shows you the platform we have to deal with. So typical constraints are that you have power of optimally speaking 1.5 watts, a little bit more, depending on the type of satellite you're trying to use this instrument for, low mass and low volume. So these are tough constraints on such a radiation device. So what I've mentioned before translates directly into the following problems if you were to implement the front-end electronic processing steps using discrete components. Because for every detector you have in this radiation monitor, you would need to use a number of discrete components. Simply your instrument wouldn't fit into a CubeSat. So you have a large required volume, you have a large number of components which can fail, and this also translates usually to a large power consumption and heat dissipation which cannot be dealt with. So this classical approach is nothing we can really use besides as demonstrations for nuclear physics courses or such. So the opportunity, what I'm going to talk about, is taking most of the steps of the front-end electronics processing chain and put it into a monolithic integration. This means we put it all on a application-specific integrated circuit, which can just fit on the thumb of your hand. I have been given one such readout ASICs, and I'm currently studying my project how to implement this ASIC for CubeSat missions. By cutting the whole processing chain short, as you see here in this modified processing chain, most of the data analysis from the physical sensor to your onboard computer system is being done inside of the ASIC, which highly simplifies the implementation of a radiation monitoring device. So we get for free a small form factor, low mass, power, and also radiation hardness by design. In addition, we are able to upscale the number of sensors, hence parameters we can study, as we get multiple readout channels available. Now a few words about my project. At our university, we have been investigating what we are going to do after our NUTS CubeSat mission. And for this, we've been investigating to propose several instruments for future missions. I'm working in a master thesis in a collaboration with an industrial partner, which is the Integrated Detector Electronics IS, short IDEAS, and I'm implementing a prototype of this compact space radiation monitor using the VADA 465 ASIC, which is a readout device. You see on the right-hand side a sketch of this project. So you have a sensor on the top left. It could be any silicon diode. You could use any technology you want, silicon strip detectors if you want positional information. You can have many detectors as a particle telescope, so you stack them on top of each other. That's really a matter of the scientific objectives behind it. However, I'm more dealing with the electronics. The sensor is then connected to the ASIC, which in turn needs to be programmed and controlled and interact with an FPGA, a field programmable array. So this gives you the capability which a microcontroller, which is usually used, cannot provide, because you have it's too slow, it's not parallel sequential, programming and execution. And then later on in this test setup, I interface the FPGA with PC, but this can be the onboard computer system. The issues. Everything I've said would indicate and raise the question, why haven't we done this before? I can tell you people have done this before, and unfortunately not very successfully. I think I have seen last year in the symposium there was a presentation from Turkey, and I'm very curious to hear what their results are on X-ray detection, which is somewhat similar to what I'm presenting here. But in general, it has been found difficult to actually implement this technology, which is well-known in high-energy particle physics, on a CubeSat, on a small satellite platform. So this is highly interesting. The problems are as follows. It is expensive to create an ASIC which you can use on a space mission. It is very expensive, actually. So what needs to be done is that you rely on existing technology, which is done in this project. Then you have overheating, overhead, which can come due to FPGA software development, which cannot be trivial unless you're very well trained in it. But it also gives you opportunity to implement the entire onboard computer system aboard a powerful FPGA, so to create a system on a chip type, which would be very interesting. I think this would be something to look at as well. The FPGA may also require more power than a microcontroller-based design. But it compensates for that you can do better science with it. And now I come to the conclusions. I've presented to you a compact electronic design for radiation monitoring instrument. It gives us the capability of having such instrument coming with low power and giving us the opportunity to do multi-channel applications, to do relevant scientific data acquisition with such instrument. Prototyping of the implementation is currently going on at NTNU, and we're aiming to create a standard component for future satellite missions, such as the Norwegian NorthSat-2 mission. This is very interesting. I want to share this with you, because if you have many of such instruments, which are ideally very small and compact, you could use it to complement very expensive missions in the study of space weather and as protection for satellites, and as well as having a better understanding and modeling of the existing theories. So this would be very interesting, and I'm inviting you to take this input and contact me if you have any questions or you're interested in implementing such an instrument. I thank you for your attention, and I would like to acknowledge the support of my university, NTNU, the European Space Agency, for sponsorship, and EDS. Here are my contact data. If you have any questions or feedback, please let me know. Thank you.
Thank you for your presentation. Please.
I guess you have some tests already with that kind of front-end electronics. What kind of sensor did you use for tests, and what kind of energy range can you address?
So the issue is the current state of the project is more on the development of the FPGA, so I haven't hooked up a real silicon sensor to this yet. This is all just in the lab where you have a capacitive coupling to a voltage source, which gives you the right current passes. So I can't say anything about a concrete silicon sensor attached to it. We were investigating silicon sensors and also cadmium zinc telluride. So, but it needs to be done.
No idea about the energy range?
Well, it depends. It usually depends on the sensor you're using. So energy range would be probably 1 to 20 mega electron volts for electrons, and something in the range of 20 to 120 mega electron volts for protons, in using standard components. So, yeah, but that's more a question of the final instrument implementation. So this is about front-end electronics. I hope I answered your question. Any other questions?
Just to let you know that front-end electronics, ASICs and SSDs are used already in many NASA missions, starting from Cassini from MMS, from Radiation Telescope probes. And so it's to say this. So the question here is what we want to do mostly, and I will go to the energy range the previous question was about. If it is a radiation dose or it's a science instrument. So those are the kind of discriminating factors when you are using an ASIC, especially this idea of ASIC which people use also in flight missions. So it's not something very new, but you have to find the right niche of application and do the right electronic costing for this application. So it's, and most of the issue here is in the analog electronics, not usually in the digital electronics. So.
Yeah, so it was more comment. I can comment back on that comment. So we have currently we are studying the opportunity of looking into a particle telescope. So you would stack many of these sensors, and you would do energy discrimination in this way. It's very coarse, but it would be interesting to implement since there is an ESA mission named JUICE to study the Jovian moons, and they want to use something like that. And we were thinking of implementing a test on the balloon mission for now. So, but yeah, I agree. It depends highly on the science. That really is the main, how to say, the decision maker here. And it's new in CubeSats, so that's clear.
Okay, thank you very much. If you have any other question for Mr. Stein, please address it during the lunch break. Thank you very much for your presentation.
Thank you.